Vector spaces of a graph. Modern abstract algebra is a powerful tool in the theory as well as in the application of graphs. So it is essential for a thorough understanding of graphs. It's necessary to represent a graph algebraically, and if you want to solve graph theory problems using computer, then it is necessary to take graph theory, learn graph theory algebraically and manipulate it algebraically. So let us look at graph theory through linear algebra concept. Initially, we show that sets of certain subgraphs of a given graph, they form their groups, okay, and these are very fundamental and important results in graph theory. I can say a cycle space, which is nothing but set of cycles, they also form a vector space, and edge space, vertex space, they are also vector space. So first we'll prove a theorem that states the ring sum of two circuits in a graph is either a circuit or an edge disjoint union of circuits. To prove this, let us take two circuits of a graph G. G is my graph. See, here we are dealing with undirected graphs, okay. We are dealing with vector space of a undirected graph. Let G be my undirected graph, and say gamma 1 and gamma 2 be any two circuits in graph G, okay. See, if these two circuits may have a common edge or common vertex. If they don't have, like if the two circuits have no edges or vertices in common, then their ring sum gamma 1, we know what is ring sum, gamma 1 plus gamma 2 is a disconnected graph. See, if they don't have any edge or vertex in common, simply if my G is, for example, this is my graph, say this is one circuit gamma 1 and gamma 2 in my graph. Now they don't have, this circuit and this circuit, they don't have edge or vertex in common. But when I take their ring sum, then it will be a disconnected graph. So I can say it is edge disjoint union of circuits. This gamma 1 ring sum gamma 2 is edge disjoint union of circuits. If suppose they have some vertices or edges in common, then the result is different. So how we'll show what happens if gamma 1 gamma 2 share a common vertex. So case 1, if V is a vertex which is in gamma 1 only or in gamma 2, okay. If V is any vertex, it is either in gamma 1 or in gamma 2. Then what happens? Degree of this V should be 2 in gamma 1 ring sum gamma 2. See, if this vertex V is over here, when I take gamma 1 ring sum gamma 2, how that is, this is a disconnected graph. This is gamma 1 and this is gamma 2. Ring sum means they have all the vertices of gamma 1 and all the vertices of gamma 2, but the edges either they have to be in gamma 1 only or in gamma 2 only. There should not be edges which are in common when I take gamma 1 ring sum gamma 2. This is a disconnected graph in this case. Even if I take vertex V is in gamma 1, okay, or in gamma 2 only, then its degree must be 2. This is an example, okay. It must be 2 in when I take a ring sum of gamma 1 and gamma 2, because I know in a circuit degree of every vertex is 2. Okay, this is the case 1 when I say vertex is in common. Vertex is either in gamma 1 or in gamma 2. Case 2 is if an edge is in common to gamma 1 and gamma 2. An edge is in common to gamma 1 and gamma 2. Suppose it's something like this. Okay, suppose this is my circuit gamma 1 and this is another circuit gamma 2. Okay, they have common edge. So when I take the ring sum gamma 1 ring sum gamma 2, then there will be something like this. This edge won't be there when I take ring sum. So in this case also, degree of vertex, whether this vertex, any vertex if I consider, then degree of V is 2. Okay, when I take ring sum, in this ring sum, degree of any vertex if I consider, that is 2. So the next case is if gamma 1 and gamma 2, they just interacted to vertex say V. Okay, what happens if they interact at a vertex V like this? This is gamma 1, say this is gamma 2, no? Gamma 1, gamma 2, and they interact at a vertex V. Okay, when I take their ring sum, number of vertices is same and that will remain same, and edges in gamma 1 and edges in gamma 2, they must be there in gamma 1 ring sum gamma 2. So this is same as ring sum gamma 1 with gamma 2. So what happens to degree of this vertex? Degree of this vertex is 4. So I can say degree of V is 2 if V is in gamma 1 only or in gamma 2 only, or if one of the edges formally incident on V, any vertex V formally incident on V was in both gamma 1 and gamma 2, means that edge including this vertex V is in both gamma 1 and gamma 2. In these two cases, I am getting degree of that particular vertex as 2. Okay. If gamma 1 and gamma 2 just interact at a vertex V, I am getting degree of vertex as 4. So, what I can say, in each case, degree of every vertex in gamma 1 ring sum gamma 2 is even. Is even every time. Degree of every vertex in ring sum gamma 1 gamma 2 is even, and I can say when I have every vertex is of even degree, then this must be an Euler graph. We know in Euler graph every vertex is of even degree. Hence I can say that ring sum gamma 1 gamma 2 can be either a circuit or an edge disjoint union of circuit. Hence the proof. So now we have proved ring sum of two circuits is either a circuit or an edge disjoint union of circuit. Now I'll take set of all the circuits and the edge disjoint union of circuits, and I want to prove that this form an abelian group under the ring sum operation. So the theorem that says the set consisting of all circuits and the edge disjoint union of circuits including the null set or null graph phi in a graph G is an abelian group under the ring sum operation. So let us prove this now. So what has to be true when I say, when I have to prove any set is an abelian group? I have to prove 5 axioms, that is closure law, associative law, identity law, inverse law, and commutative law. So let us take set of all circuits and edge disjoint union of circuits. Let me define that as, say, set M, which is set of all cycles or circuits and edge disjoint union of circuits. Edge disjoint union of circuits. M is a set of all cycles and edge disjoint union of circuits. So first we'll prove closure property. If I have gamma 1 and gamma 2 are the two circuits in my set M, then we know that ring sum of any two circuit is either a circuit or an edge disjoint union of circuits. So what happens when I take ring sum of gamma 1 and gamma 2? Of course it is a circuit only, therefore it should be in M. So closure law holds good. Closure law holds good. And next is, if I have gamma 1, gamma 2, gamma 1, gamma 2 and gamma 3 in my set M, then of course their ring sum I am taking gamma 1 ring sum with gamma 2 ring sum gamma 3. This is again a circuit, and this circuit with this again form a circuit. And this is same as gamma 1 ring sum gamma 2 with the ring sum gamma 3. Therefore, I can say that associative property holds good. So when I come to identity, a null graph, this is a null graph, null graph is an identity element in M. It is an identity element in M. Since for every circuit in gamma, in M, I can say ring sum of this circuit with this null graph gives me the circuit itself, and of course it belongs to M. So identity property holds good. When it comes to inverse, we know that ring sum of a graph with itself is a null graph. So for any circuit gamma belongs to M, gamma ring sum with itself gives me a null graph, which is an identity element in M. Therefore inverse of gamma is gamma itself. So inverse property holds. There exists inverse for every circuit, that is itself. And the last property is commutative property. If gamma 1 and gamma 2 are in M, then of course we know ring sum, I can take it in any order. Ring sum of gamma 1, gamma 2 is same as ring sum of gamma 2, gamma 1. So commutative property holds good. Thus I can say that M, which is a set of all circuits or edge disjoint union of circuit, forms an abelian group under the ring sum operation. In the similar manner, I can even prove that set of all cut sets or edge disjoint union of cut sets forms the abelian group under the ring sum operation. The same for the representation of graph, we are concerned with only a field which is nothing but a Galois field. Say this is denoted by GF of 2, in the sense Galois field mod 2. In fact, it is nothing but when I take set Z2, which has got number 0, 1 in the set. Okay, it forms a field with respect to addition mod 2 and with respect to multiplication mod 2. In fact, this multiplication is usually denoted by dot. Okay, and this Z2, this set forms a field with respect to addition mod 2 and multiplication mod 2, and that's this field is called Galois field. In fact, the truth table is, when I consider addition, if I take 0 and 1, this is addition 0 and 1. Okay, 0 0, it is 0, 0 1, it is 1, 1 plus 0 1, 1 plus 1 is 2. When I take with respect to mod 2, it becomes 0. This is the truth table for addition. And when I take multiplication, 0 1 0 1, this 0 into 0 is 0, 0 into 1 is 1, 1 into 0 is 0. 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 1. In fact, if you know Boolean algebra, then this is nothing but exclusive OR, and this is nothing but AND gate. We don't want that. We just have to know what is Galois field. It's a set of numbers 0, 1, which forms a field under addition mod 2 and multiplication mod 2. Now, in fact, if I have set any set ZM which has numbers 0, 1, 2 up to m minus 1, then with respect to addition mod m and multiplication mod m, they form a field if and only if m is a prime number. Okay, such fields are nothing but the Galois field, and is usually denoted by GF of m. GF of m. In study of graph theory, we are dealing with only Galois field mod 2. Okay, so let us look at vector space now. Vector space. What is vector space? Any set, a non-empty set V over a field F, over the field F, is said to be a vector space if for any two vectors v1, v2 belongs to V, there is a defined unique sum, that is v1 plus v2 in V, and for any alpha belongs to F and vector V belongs to V, such that alpha into V belongs to V, they satisfy, see, addition is defined and multiplication is defined like this. If this satisfies the following 5 conditions, then I can say that a set, non-empty set V is a vector space over the field F. What are the 5 axioms in fact? One thing is this V, set V, should form an abelian group under addition. It must be an abelian group under addition. It must be an abelian group under addition. And if I take alpha is in field F, and if I take V1 and V2 as the vectors, then alpha into V1 plus V2 is alpha V1 plus alpha V2. And if I take alpha and beta in field F, if I take this, alpha plus beta into V1 is alpha V1 plus beta V1, and alpha into beta into V1 is nothing but alpha into beta into V1. And at the end, if 1 into V is equal to V for any alpha beta belongs to, this I have already mentioned, for any alpha beta belongs to F and V1 V2 belongs to W. If this is satisfied for all the vectors in set V, then I can say that set V is a vector space. Examples for vector spaces, if I take a set of two tuples, means say x1, x2, that is R2, belongs to R2. Then it forms a vector space. Like that I can take n tuples, they also form a vector space or a real number. Now, to study vector space associated with the graph, we are representing graphs in terms of these tuples. Okay, so that we any graph G, we can define a vector space associated with that graph. Okay, so let us learn that. Let us consider a graph G, okay, with 4 vertices and 5 edges, say E1, E2, E3, E4, E5. Now, I am taking set VG, okay, which is all set of all subgraphs of G, including the null graph and the graph itself. Okay, it's a set of all subgraphs of G, which includes a null graph and the graph itself. In fact, how many subgraphs are there? 2 to the power 5 subgraphs are there. Okay. Now say this is G1, G2, there may be many more. Okay, I am just taking 2 in this case now. Okay, now I am representing these subgraphs using the phi tuple. Okay, phi tuple means, say this is like this, phi tuple is like this, x1, x2, x3, x4, x5, such that this entry x1, I am defining over a Galois field. Okay, this entry x1 or xi is 1 if an edge ei is in G. Okay, and this entry is 0 if ei is not in the subgraph G. Okay, so I am representing these subgraphs using n tuples based on this condition. Okay, so how is G1 now? G1 can be represented as, using a n tuple, it can be represented as E1 edge is there, therefore 1, E2 is not there, so 0, E3 is there, 1, E4 is not there, and E5 edge is there, therefore xi entry is 1. So G1 is represented by 1, 0, 1, 0, 1. Similarly, I can represent G2 also. Now, if to represent G, how can I represent G? All edges are present. So 1, 1, 1, 1. And a null graph is denoted by, which is also a subgraph of G. So it is denoted by 0, 0, 0, 0, 0. Now say I have taken G1 and G2, I'll just write it how it is. G2 is, E1 is not there, E2 is there, E3 is there, E4 is there, and E5 is not there. Okay. Now I can write their ring sum, G1 ring sum, G2. What happens to the ring sum? G1 is 1, 0, 1, 1, 0, 1, 0, 1. Yeah, it is G1. I'm taking its ring sum with 0, 1, 1, 1. G2 had E2, E3, E4, right? So E2, E3, E4, E5 was not there. Okay. So their ring sum I'm considering now G1 ring sum G2, which is nothing but 1 1 0 1 1 1 1 0 1 1. So in fact it is E1, E2, E3 is not there. E3 is not there. E4 and E5. G1 ring sum G2 is the set E1, E2, write like this, E1, E2, E4, E5. This belongs to my VG. VG is set of all subgraphs, so this also forms a subgraph. So we can show that VG forms an abelian group with respect to ring sum operation. This is how we have to do the ring sum operation, and I can show that set of all subgraphs, they form a vector space, they form a abelian group with respect to ring sum operation. Now I can define, say, 0 into Gi, any subgraph, as a null graph, and I can define 1 into Gi, means that is the subgraph itself is a subgraph itself, and we can easily observe that the scalar multiplication defined above is well defined in fact, and they obey the postulates of a space, vector space. Thus I can say VG forms a vector space, and it is the vector space associated with the graph. So for any given graph G, we can define a vector space associated with it. When we are studying vector space, we also should know what is basis of a vector space. Before that, we should know what is linearly dependent vectors and linearly independent vectors. Suppose I have a set of vectors x1, x2 like that, xn over some field, say f. To say that these vectors are linearly independent, if for some scalars, say c1, c2 dash dash cn in f, the expression c1 x1 plus c2 x2 dash dash cn xn equal to 0. This is equal to 0 only if all Ci's are equal to 0. C1 equal to C2 dash dash equal to Cn equal to 0. Otherwise, this set of vectors are called linearly dependent. I repeat, a set of vectors x1, x2, xn over a field f is said to be linearly independent if for some scalars in the field c1, c2 dash dash cn, this statement holds good only if all the constants are scalars are equal to 0. If this is not so, means all are not equal to 0, then I can say that these vectors are linearly dependent. For example, I can check whether the set of vectors are linearly dependent or not. Say I have a vector x1, for example, x1 is 1, 4, 0, x2 is a vector 0, 1, 2, x3 is 3, 0, 0. Okay. I am taking an arbitrary linear combination, okay, of these three vectors, and I know they have to be equal to 0. Suppose c1, c2, c3 are the constants, scalars. c1 x1 plus c2 x2 plus c3 x3 is equal to 0. So that is nothing but, so I am getting c1 x1, c2 x2, c3 x3, it is equal to 0 means 0 vector. Okay, from this I can say C1 plus this system of equation I am getting C1 plus 3C3 is equal to 0. 4C1 plus C2 equal to 0 and 2C2 equal to 0. So 2C2 equal to 0, this implies C2 equal to 0. So when C2 is 0, I can say C1 is also 0. When C1 is 0, C3 is also 0. So what I can say is these three vectors are linearly independent. Similarly, I can give one more example. So in this example, I'm not getting anything directly equal to 0. Okay, I'm getting C1 plus C3 equal to 0. So I just use this. Okay, I'll take this can be rewritten as this term. This equation can be rewritten as C1 is minus C3. Okay, I got C1 is equal to minus C3. I'll apply in this. The equation is 2C1 plus C2 minus C3 is C1. Okay, which is equal to 0. So far I got 3C1 plus C2 is equal to 0. Now 3C1 plus C2 is equal to 0. If I take in this C1 is minus C3, then I'll get C1 plus 2C2 minus C3 is C1. So C3 is minus C1. So I am getting 2C2 equal to 0. So C2 equal to 0. I'll put that in this so that C1 becomes 0. Hence I can say C3 is equal to 0. Therefore I can say these vectors are linearly independent.